Bismillah ar-Rahman ar-Rahim. So we started talking this chapter about line coding schemes. So we talked about categories of line coding schemes. We talked about unipolar schemes like non-return to zero, and then we talked about polar schemes like also non-return to zero, and also the biphase and so on. And we also talked about the bipolar schemes, and there is only one line coding in this category, which is the AMI, where we can use three different levels. Zero is one of them, so we have positive and negative, and the zero is one of them. And then we have started talking about the multi-level schemes. Of course, for each line scheme, we would just try to analyze the scheme with respect to the criteria that we have, the baseline wandering, the DC component, the self-synchronization, and so on. So, for example, this multi-level scheme, as we said, it's part of the MB-LN schemes, and as we said, 2 to the power m has to be less than or equal to L to the power n. And if we have equal, this means that we do not have any degree of freedom. So we always have one bit combination mapped to one signal element combination. So we do not have any degrees of freedom, in which case we will probably end up with a DC component, as well as we will lose the self-synchronization if we have repeated the bit combination, like all zeros, or 0, 1, or 1, 0. Any of these bit combinations, we would have straight line, in which case we will lose the self-synchronization feature. And we have talked about, for this particular scheme, by having two columns here and make it relative, at least we can eliminate the issue of the self-synchronization for part of the bit combination, similar to the differential non-return to zero. So here, if we have, for example, 1 0 1 0 1 0, okay. So if you have repeated 1 0 1 0 1 0, then for the first time it will be -1, right? And then because it's -1, the next one is going to be negative. So we go here, so we make it +1. Okay, and because this is positive, then we will jump here. So at least for repeated 1 0 1 0 and repeated 1 1 1 1, we can have some alternation. So at least we reduce the effect of self-synchronization by having this second column, similar exactly to what we have done for differential non-return to zero. We talked about this scheme, the 8B6T, in which case there are some degrees of freedom, and we try to use these degrees of freedom to eliminate some signal elements that have more polarized positive versus negative. So for example, here we will try to use the bit element combinations that have number of negative values equal to number of positive values somehow, because we have many combinations of signal elements in that case, because the 256 here is much less than the number of bit elements that we have. So we have some room to use some of the elements that have good features in terms of positive and negative. So this way we can try to reduce or eliminate the DC component, okay, and also enhance the self-synchronization feature. Also here, because we have here number of negative elements 2, a number of positive elements 3. Okay, so here 1, 2, 3, and here we have 2. So this is again, this will add some DC component. So in some cases, because this bit combination will have also another signal elements with 3 positive values and 2 negative values, which will add another DC component. In which case, we use the concept of reverse polarization. So we use inverted pattern. So we will multiply this by -1. And I have to inform the receiver that this pattern is actually reversed. So by doing that, the number of negative elements here is 3, and here is 2, and here the positive is 3, and here is 2, so they balance each other. So that overall, I have DC component of 0. I don't have any DC component. مفهوم دي? So in some cases, we use this inverted polarization to balance the positive and negative values in order to eliminate the DC component. So for this scheme, so first of all, we notice that the scheme has a different name, different terminology. So it's a multi-level scheme. However, it uses the concept of modulation or digital modulation. So it uses the pulse amplitude modulation. So this is a 4-dimension, which means that it actually, first, it should have 5 levels. So it should have like two negative levels and 2 positive levels and the 0. Okay. However, for this scheme, the first thing we need to know is that the 0 is actually used separately by a separate line, which can be used for enhancing error detection. So this scheme should have 5, but it actually has, because here it's 5 levels. But in fact, it uses the 5th level for error correction and error enhancement. So here we have only 4 levels. And we also have 4 elements, 4 signal elements. So we have 4 levels and 4 signal elements. So how many signal element combinations we have? How many signal element combinations we have? What is L to the power n here? 4? We have 4 levels and we have 4 different elements. So how many? 4 to the power 4, right. So 4 to the power 4 is actually 256. And what is, again, the bit combination here? So we have 8 bits. So how many combinations we have? 2 to the power, which is also 256. In other words, the only degrees of freedom we have is actually in the 0 that we have eliminated, and we used it for error detection. Other than that, the 2 to the power m equals to L to the power n. Okay, so here we also have 2 to the power m, which is the number of bits, equals to L to the power m. So here 2 to the power 8 equals 4 to the power 4. So one thing we notice here is that this scheme is significantly different from what we have studied before. So the first thing they do is that they actually separate the 4 signal elements in 4 different lines. Okay? So each of these signal elements will be sent on a separate wire. And that's why we keep telling you for Ethernet, we have, remember we have 8 parallel wires, right? Well, 3 of them are used for control. Okay? And actually 4 of them are used for control. And the other 4 are used for a separate stream. Each of these streams is actually one signal element that represents, collectively they represent 8 bits. So this is used for gigabit Ethernet. So this scheme is used for gigabit Ethernet. Okay, so we said that the signal, we said that here the signal rate equals to C, which is half, multiplied by n. So if n is 1 gigabits per second, then the total signal rate is 500 megabits per second. And what they do is that they divide these amongst the 4 lines, so each of them will have 250 megabits per second, and therefore the signal rate for each one is 125, which is half this. Okay, so the signal rate will be 125 megabaud for sending 250 megabits per second. So they actually separate between them. Okay, so that's I think that's all. So the only difference here is that we have to separate the 4 signal elements in 4 wires. Okay, type. So this is for the multi-level category. And for multi-level category, as we said, if we don't have any degrees of freedom, then we end up with issues like DC component and the self-synchronization or lack of self-synchronization. But if we have more degrees of freedom, then we can use these signal combinations to try to enhance the error detection and the self-synchronization feature. Another category, which is slightly different, which is what we call multi-transition. So in this case, we are not using multi-level per se. It's similar to the bipolar. So we have 0 and we have positive and negative. So similar to bipolar. However, it also combines the concept of transition. So depending on the previous bits, we have to transition to a different voltage level. So the multi-transition scheme here, it works based on these rules. So the first thing is that if the next bit is 0, then whatever level you are at, just stay the same or keep it the same. Okay, so for 0, we have to keep it the same. Of course, in that case, we have the issue of, again, we have the issue of DC component. If we have repeated zeros, then we have DC component. And if we have repeated zeros, we also have the lack of self-synchronization for this case. But if the next level, if the next bit is 1, now it depends. Okay? If the next bit is 1 and the current bit is 0, is not 0, sorry, then you go to 0. Okay? So if you are at this level, for example, and the next bit, so here, the next bit is 1. Okay? So if you are at non-zero level, go to 0. Okay? If you are at 0, then this is the third rule. If you are at 0, then you have to look at the previous non-zero level. If it's positive, go negative. If it's negative, go positive. So logically, what this tries to do is, again, tries to balance the positive and the negative. Okay, so we can reduce the DC component and we can enhance the self-synchronization. However, with only 3 signal levels, we cannot do much. We don't have enough degrees of freedom to eliminate it in every bit combination. So we still have some DC component if we have straight zeros. So we know that, right? So what is the benefit here? So we have talked about before. We have talked about non-return to 0. If you remember, the non-return to 0, it had some benefits similar to this. However, it didn't have the inversion in case of if the next bit is 1. So just to appreciate the benefit that we have in this case. So imagine if we have straight ones. Okay, if we have straight ones, then what we will end up having is that if this is positive, then if the next bit is 1, then we go a 0, right? Because it's a non-zero voltage level. Then we go to 0. Then we ask ourselves, the next bit is 1, and we are at 0. Then we have to look at the previous non-zero voltage level. It's positive, then we have to go negative. Then we are at negative or non-zero voltage level. And the next bit is 1, so we go 0. Right? So we keep doing that. And as you can see, in comparison to the non-return to 0, which will produce straight voltage level, here we have converted the fixed voltage level into a periodic digital signal that looks like it can be represented using an analog signal with low frequency, as you can see here. So you can sort of represent this using an analog signal that looks like this if we were to approximate it, right? And because of this period, we can represent this using a periodic signal, a periodic analog signal with low frequency. In other words, suppose that we forget about this and we calculate the signal rate. What is the signal rate here? So what is R? What is R? R is A? 1. No? R is the number of data elements divided by the number of signal elements. So it's 1 divided by 1. So R is 1. R here equals to 1, right? So ideally, the signal rate equals to the case factor multiplied by n, right? So it should be, if we were to use the case factor of half, then it's n over 2. However, because of this notion, because of this concept, C is actually less than half. Because what is C? C refers to the average case. So C is actually calculated based on the fact that you have different bit combination from the input side, and then for each time you have to calculate the number of changes in the signal. The number of changes in the signal. Okay? So if the probability for non-return to 0, for example, if it's based on mapping absolute bit, 1 bit to an absolute voltage level, regardless of the previous one, then the possibility of having any signal level is on the average the same. In which case the case factor is close to half. However, for this case, because of what we have done, the case factor is not actually half. It's less than half. So it tends to be around, so the case factor here tends to be around 1 over 3 because of what we have done, which means that the signal rate will be around n over 3. Okay? So because of this concept, the signal rate is less, which means, of course, that the bandwidth is less, right? So this is the main benefit of this of this scheme. What is the cost that we have paid? Well, it's more complex. Well, it's more complex. Sometimes you have to, for a particular voltage level, for this one, we have to go back to see what is the non-zero voltage level in order to find the next one. So sometimes you have to go back several positions until you figure out. So this adds to the complexity of the transmitter, of course, right? So that's the cost that we have paid. In muqabil, what we have gained is a low signal rate. Okay? So that's the only scheme in this category, the multi-transition. So this is the summary of all the schemes that we have talked about. So we have the unipolar, we have the polar, and we have bipolar, multi-level, and then multi-transition scheme. So we notice here that the bandwidth is actually n over 3, or the signal rate is n over 3. For this one, as you can notice here, it's not n over 2, as we said, right? It's n over 8. The reason for this is the split between the lines. Because when you split the lines into 4 parallel lines, again, you reduce the case factor drastically by having these parallel lines. That's why they actually separate them. So actually the bandwidth is n over 8 because you have separated the signal elements across 4 different lines. So you divide by 4. Okay? So this is the characteristics of each of these, which we have gone through in details. So here we notice that for the one that we have just discussed here, no self-synchronization only for the case of A of 0. But for the case of straight ones, we have been able to create a very nice periodic signal, which has actually contributed to the fact that the signal rate is n over 3. Okay? So any questions for the line coding? Of course, just the fact that some of these schemes, they have problems with the DC component and the self-synchronization, it doesn't mean that they are not used. Okay? So they can be used, and actually, in the next slide, we will talk about block coding. And block coding is actually an optional component which can be added with the line coding, okay, in order to make up for the problems in the line coding scheme. So if you don't have, like for example, if you don't have self-synchronization, you can use block coding to make up for this, or to enhance the self-synchronization feature. Okay, so that's the benefit of block coding. Also, block coding can be used for error detection, for enhancing or improving error detection. And we'll talk about how we can do that. So block coding is referred to as MBNB. And there is a slash here to try to distinguish between this and the multi-level. So in the multi-level, we had the multi-level, we had M, B, N, L, right? So this is the multi-level scheme. So depending on changing M, changing N, changing L, we have different schemes, like the 2B1Q, which is what we talked about. So here, to differentiate the two schemes, so when you see this, you know that it's a multi-level line coding. When you see MB and B and slash in between, so this means that it's block coding. It's not line coding, it's block coding, right? The other thing is that M is always more than or equal to N. So N is more than or equal to M. Always. And why is this? We'll talk about this. So as we said, line coding, what happens is that we take the stream of bits, and then the first thing we do is that we divide these bits into M groups. Multiple groups. Each group is of size M. Okay? Like for example, we take 4 bits. We put it in one group. Okay? That's why it's called block coding. And then we map this M bits into N bits, such that N is more than or equal to M. When we do that, what do? What we have essentially done is that because we can map M bits into N bits such that N is more than M, what does that mean? This means that by doing that, we have increased the degrees of freedom, right? Because if you have, for example, like 4 bits, how many combinations do you have in 4 bits? 16, right? If you convert it into 5 bits, how many combinations do you have in 5 bits? 32, right? So we have actually doubled the number of combinations, right? So this degrees of freedom, similar to what we have done before, we can try to use it to improve the self-synchronization. Okay? Similar to what we have done before. So we will try to select the combinations such that the number of ones and the number of zeros are more or less the same. Okay? So when we have like straight zeros, 4 zeros for example, we want to avoid this. So in the fifth bit, we try to insert 1 in between. Something like that. So by doing this, we have introduced an alternation in the bit. Okay? And we try to avoid, of course, all the cases when we have 5 ones or 5 zeros. These combinations, we will not use them for mapping. So, because we have 32 combinations, right? So we can eliminate 16 of them and use the other 16 that have nice feature in terms of the number of ones and the number of zeros. So we try to enhance or increase the alternation in the bits. So this is the main idea of the block coding in particular. Okay? Of course, we have another 16 combinations, right? So these 16 combinations, we can use them for signaling that can enhance the error detection. That's why we said that block coding has 2 functions. One is that it improves the self-synchronization by imposing some alternations, right? So when we have straight zeros, we put 1 in between. If we have straight ones, we put 0 in between. So to try to add some alternations in the bits. The other thing is that all the unused combinations in the block coding, we can use them for signaling to enhance the error detection. So this is the main idea. So what we do is that, because we know that non-return to 0, for example, the non-return to 0 line coding, if it has straight zeros or straight ones, if you remember, for non-return to 0, if you have straight zeros or straight ones, sometimes it makes a problem. Okay? So to avoid this, before we apply the non-return to 0, we can apply block coding on the input bit stream. So on the input bit stream, we can try to see each four bits, we will convert them into 5 bits. Okay? And the 5 bits will have some alternation. So when we do this, then we can apply the non-return to 0, and we're comfortable that we have enough alternations that we will never have straight zeros or straight ones. We will never have this case, right? So by doing the block coding before the non-return to 0, then we can enhance, not perfect, but we can enhance the self-synchronization feature of the non-return to 0. What is the cost that we have paid here? What is the cost? What did I pay?
Quality.
Quality of what? Yeah. So when we go from 4 to 5, what we added a block. Come on, we added a full block. Time overhead, time and overhead. Overhead, why? Because we converted each 4 bits to 5 bits. So what is the overhead here? It's 1/4. We added 25% overhead. So you have specific number of bits coming, you added 25% to these bits before you try the non-return to 0. Okay? In order to gain those 2 features, the self-synchronization and the error detection. Okay, so we had to pay some cost. Of course, we have to do the block decoding at the other side to revert back to the original. So that's how it looks like. So the input itself will have all the combinations. So we have 16 input bit combination. So we will map these into the 5 different bit combination here, such that the number of zeros and ones is actually more balanced. So for example, here we have straight zeros. We convert that into 4, 1, and then 0. So at least we have one change. So the number of changes between the 1 and 0 is always here much more than here. Okay? So here, for example, we have 3 zeros. Here we have 0, 1, and then 0, and then 0, 1. So we have how many changes? Here we have only one change. Here we have 1, 2, 3. Okay? So at least by doing this change, we can trigger the non-return to 0 to have more alternation in the signal, which will add some self-synchronization.
Yes, Doctor. The first one, the data set is all 0. So why we don't insert only one bit, like 0, 0, 1, 0? So
we are free. I mean, we have 32-bit combinations that we can select from. We will select the 16 that have good number of changes between them. So here we have no change, we have 0 change. Here we have introduced 1 change. Okay? So it's mapping. In any case, we will have to map. And we're not inserting. This is different from inserting. Block coding talks about mapping an input bit combination to an output bit combination. It's always mapping. It's not inserting something in between. Okay? So we have all the freedom to do this mapping in any way we see appropriate, right? And we'll do it in such a way that will increase the number of changes in the bit. And of course, we will end up with another 16-bit combinations that are not used. And in that case, we can use them for signaling. So by doing these signaling or control signals, we can improve the error detection. Okay? So we studied that in 455, if you remember. We talked about that. So that's the block coding. This is like an idle transmission. This is halt. This is start delimiting or something like this. So we can use that for frame delimiting. Remember, we have from the data link layer, we have frames. So we actually use these signals to mark the beginning of a frame, end of a frame, and so on. That despite the fact that we add some changes, still the number of ones and the number of zeros are not the same. So that's why we did not say that this actually eliminates the DC component. What we have claimed is that we have enhanced the self-synchronization, right? But we did not talk about DC component here. So what this type? So this is how it looks like, the substitution part. So the substitution part, so you have the input number of bits, and you take 4 bits, and then you map them, into 5 bits, based on the lookup table that we have before. And then we keep doing that until we have all the mapped bit stream, and then this mapped bit stream will feed it to line coding. Okay? And then after line coding, we transmit it over the line. This is what we call a baseband transmission, because we convert the bits into digital signal. So this is baseband transmission, and we transmit it over the line. On the other side, we have to detect the signal, and then from the signal we convert it into 5-bit combinations, and then we revert back by mapping the 5 bits back into 4 bits. Okay? And any signal that does not represent one of the input bits, we recognize it as a control signal. So we know that we can do like, we know that there are some cases, disparity control. So similarly, we can take each 8 bits instead of 4 bits and convert them to 5. We can take 8 bits and convert them into 10. And in that case, we also end up with more degrees of freedom. So instead of 256 combinations, here we have 1024 We have 10 different bits at the output. So this difference, again, we can use it for different degrees of freedom that can be used to enhance the self-synchronization and the error detection. In some cases, the designers, they try to do the 8-bit block coding as 2 blocks. Each of them is less number of bits. So you can convert the 8-bit into 2 block coding components. One is from 5 to 6 and another one from 3 to 4. Or you can use 2 blocks, each one 4 to 5. So it's exactly the same. Okay? So this way you can implement a bigger block coding scheme based on smaller components. The good thing about this as well is that it actually tries to use the disparity controller, or this disparity controller, what it does is that we have noticed here, what it tries to do is that in some cases, if it finds that the number of ones and the number of zeros are not the same, it may actually invert the output to create this balance, in which case we also reduce the DC component.
This is before the line coding?
No, after. After the line encoding. Sorry, not after the block coding as part of the line coding. As part of the line coding. So if we find that the number of ones and the number of zeros are still not equal, so we can use the concept of inversion. We can invert. And in that case, invert, we can use one of the control signals to indicate the conversion. And this way we can recover it at the receiver side. So this way we eliminate, or we try to at least reduce the DC component. So in that case, we have we can solve the self-synchronization. We can solve the DC component by doing the block coding. Of course, we had to pay some cost here. Obviously, we had to pay some cost. So we added a new block, and we have added an overhead, right? So that's that overhead has to be paid. طيب. Another concept, because the block coding, again, we have added overhead, we have added a block, and so on. So can we do better than this? Some schemes like the AMI, remember the AMI, the way it works? Of course you will not remember. The way it works is that as we said, if the bit is 0, then it's 0 all the time. For the AMI, it's 0, which is what non-return to 0 does, right? The non-return to 0, which is the unipolar version, not the polar version. Okay. So in the AMI, 0 is mapped to 0, which means that if you have straight 0, then you have a 0 all the time. So remember, this does not add to the DC component because it's 0, right? But the problem here is what is the problem here? So for DC component, it's still 0, so it does not add to the DC component, right? But what is the problem here? If we have fixed voltage, I need some interaction. If we have straight 0 like this, then we have a problem with self-synchronization. We don't have any change. If we don't have any change, then we have the problem that we cannot synchronize. Synchronization requires some changes in the voltage all the time. And we need to do that at every single bit, and that's why the biphase or Manchester encoding solves this problem fundamentally. However, as we have seen, is that it adds to the bandwidth. It actually doubles the bandwidth. So we can use Manchester encoding, okay? But here we have to pay the bandwidth, right? So the idea is that AMI, it tries to maintain the same bandwidth n over 2, and it tries to solve the problem of self-synchronization at least in one case, which is the ones. So if you have 1, then you go positive. But if you have another 1, then you go negative. Okay? And then if it's 0, you always go to 0. And then if you have 1, then you go positive. If you have another 1, then you go to negative, and so on. So at least for AMI, we try to solve the self-synchronization for the case of straight ones. But we have not been able to solve it for the case of straight 0. But at least, if we have straight zeros, it's still 0, which does not add to the DC component. So that's why AMI was kind of attractive, because for R is 1, so it's still the bandwidth or the signal rate is n over 2. Right? So from that perspective, in terms of bandwidth, this scheme is good. But the problem is if you have straight zeros. Okay? So scrambling here talks about the fact that we will try to modify AMI using the concept of scrambling. Okay? So the good thing about scrambling here is that it does not add any overhead. Okay? So we will try to do that by enhancing the self-synchronization without adding any overhead, without adding a separate block. Okay?
When we do the scramble, we don't change the data.
When we do what?
The scramble.
We change the input data, right? We change the input data, but we do not add to it. Yani we do not convert 4 bits into 5 bits, in which case we have increased the number of bits that we send. This is a clear overhead. Okay? But the idea here is that if you have straight 0, we will take this straight 0 and we'll do something about it. Okay? And we'll see how it's done. We'll do something about it without adding an extra bit. So the idea here, we have two schemes, two scrambling schemes. One is what we call B8ZS, and this is the one that's used in North America. In North America, this is the one that's used. So the idea here is that, remember how AMI works. So you have 1, and you have 8 zeros. So the sender will detect these 8 zeros. This is the sender. It detects at the transmitter side. I will take 8 zeros. If I see 8 consecutive zeros, what I will do is that I will map these 8 zeros into 0 voltage, 0 voltage, 0 voltage, and then something called violate. And then this violate, I will change the one after it to negative, and then 0, and then again to negative, and then to positive. Did I add any new thing here? I did not add any extra bit. Remember, the only thing I did is that I actually changed the 0 voltage into something like this. Obviously, what I have done here is that I created more changes, right, which enhances the self-synchronization. So that part is clear. So why did I add here positive first? Okay, this positive is actually similar to this. So why did we do this? This is called violate. Violate means that I will violate on purpose. I will violate the rules of AMI. Why? Because the rules of AMI says that if you have 0, then it's 0 voltage. And then if you have 1, then you have to look at the previous non-zero voltage. If it's positive, go negative, right? So here, I violated that. And this violation, I did it on purpose to inform the receiver that this is not a proper AMI, which means that this bit is actually not 0, is actually, sorry, not 1. You see what I mean? So I violated on purpose to inform the receiver that this is scrambling. It's not the proper rules of AMI. So this way, what I essentially did is that I violated the AMI rule to inform the receiver. I did the scrambling to create some kind of a balance. So this way, I actually enhanced the self-synchronization without adding any overhead. واضح? I did not add any overhead here. So this violate and this violate will in fact inform the receiver that this is scrambling. This is not a proper line coding scheme. So when the receiver finds this, the receiver will know that it has to map this back into 8 zeros. واضح? So that's the idea of scrambling. Without adding any overhead, I can enhance the self-synchronization, and by doing this balance, I can also reduce the DC component. I did not eliminate it, but I can at least reduce it. And that compensates or modifies the AMI, which otherwise will create a 0 voltage level, which will be very hard to recognize at the receiver side. Okay? So here, for this case, if the previous one was negative, the violate will also be negative. Okay? So this violate tries again to say that I'm violating on purpose because this is actually scrambling. It's not the proper line coding rules.
The second violate, it depends on which the second.
This one?
No,
This one?
I mean the last V.
Here?
Yeah, V. I mean V, second V.
V, yeah, the second V. Yeah, the second V is done to balance out the positive and the negative.
So the first is negative and the second is positive.
Okay, instead of doing like this, we can do it like this. Yeah, so again, this violate and this violate are used by the receiver, because if I do here negative, the receiver will start to say, okay, so I got back to the normal rules of AMI. You see what I mean here? So if you do like this, this is what you're trying to say, right? Right? This is what you're trying to say. So this will tell the receiver what? Well, okay, so since this is negative and this is positive, so this is normal. For AMI, this is normal. Right? So which means that this one is 1 and this one is 1. This is what the receiver will say. And will recognize this as an error. يعني هيتلخبط. You see what I mean? But if it finds this combination, this is violate and this is violate, okay? So this will enhance the detection at the receiver. And because it knows that it has to map each 8 zeros into this signal combination, it can detect this with high probability. But if I do only one violate, then it might be any error. So the mapping using the scrambling has to contain this violate. It's done on purpose. It's not done just like this. It's done on purpose to inform the receiver that this is indeed scrambling. It's not the proper or the normal sequence of AMI. If you return back to B all the time, then this is the normal AMI. So the receiver will say, okay, so this is the normal AMI. Okay, so it will not recognize this as a scrambling. So this mapping is essential. It's essential to be done like this. So,
Why don't we start from the first one? I mean, like, we started from the fourth zero.
this is what the next scheme will do. Because this one is less is less complex. يعني شوية less complex. We'll see the next one is more conservative. So the next scheme is more conservative. Okay, it's done on every 4 0 bits. The scheme is actually done in any all the other countries, they use this scheme. All other countries other than the US. The US always tries to be very special. So so outside of North America, this is the one that's used, HDB3. So what this tries to do is that first, instead of mapping each 8 zeros, they map each 4 zeros. And the idea here is you have to count, because we want to map each 4 zeros. Here we have to count the number of ones before that. The number of ones before we get to straight zeros. So the number of ones before this. Remember, in the other one, because we mapped 8 bits, we only had to look at this one only, right? And again, if it's negative, then we do negative violate, and then we go for mapping the other voltage level. Here we have to map the number of ones before. All the number of ones. Like if you have 8 ones, for example, then we have to go back to count the number of ones. And if the number of ones here is even, then we have to go B and then 0 0 V. So here it's a little bit tricky because the receiver has to find the V first, and then it has to go back 4 steps, okay, and map all of this to 0. Okay, so if it's even, then we start with B and then 0 0 V. And what this tries to do is obviously it tries to balance the positive and the negative, because we have even number of ones. So the even ones already are balanced for positive and negative, because according to MI, if you have 1 and then 1, 1 will be positive and 1 will be negative, right? So here we can add both of them positive to add one change only, because already the number of changes, changes here is even. So we can add all of them positive. But of course, we have to use the violate in order to inform the receiver that this is scrambling. For the case, if here the number of ones is odd, okay, then we add only one violate. So we'll add 0 0 0 and then violate to make it odd. So odd plus odd is even. Okay, so if it's even, we'll try to add odd number of positive voltage, and if it's already odd, so we add another odd to make it even. So we have again 2 signal combinations to add for the case of if the number of ones are even and if the number of ones are odd. And here it's more conservative because it maps each 4 zeros, of course, not 8 zeros. But the complexity here is that you have to go back to all the ones before you, and you have to count the number of ones. If it's even, you have a specific mapping. If it's odd, you have a different mapping. Okay? And of course here, 0 is considered even. So if you have 8 zeros, okay, if you have 8 zeros, then you will take the first 4, depending on the number of ones here, which is odd, then you map it into 0 0 V. And then the other 4 zeros, what is the number of ones here? 0. And 0 is even. Then we go back to the signal combination for the even mapping. Okay, واضح? So the difference here is that this is more conservative, and because it's more conservative, for each 4 zeros, I have to go back and count the number of ones. But again, the idea of scrambling is that you try to enhance the self-synchronization and enhance the DC component, but without adding any overhead. And this works for this case for AMI, because AMI has specific rules. Of course, other designers have tried to design scrambling for other techniques, which we will not go through. So this is the only one that we will go through, because scrambling has some complicated logic that you have to remember. And this logic is based on how the original line coding scheme works. And for each line coding schemes, you have to design a scrambling with the different properties, right? So you have to be careful about the rules for the line coding scheme, and then tailor the scrambling logic to modify the line coding schemes in order to enhance the self-synchronization without adding any overhead. So this is the main idea. Any questions? Okay. So we'll just introduce chapter 5. So for the previous chapter, what we have tried to do is that we have tried to convert the bit combination into a digital signal. So what type of transmission is this? We called it a. So we have talked about two types of transmission. We have talked about the baseband transmission and broadband transmission, right? So in chapter 4, we talked about what type of transmission? Baseband transmission. Right? Why? Because we have converted the stream of bits into a digital signal. And since we're talking about digital signal, we have low frequency component, we have zero frequency component, and this is what we have called baseband transmission. For baseband transmission, we require the channel to have a low pass behavior, right? Analog transmission here talks about the case of broadband transmission. So in this case, we will convert the input bits into analog signal, not a digital signal, which is what the line coding scheme and the block coding and all of this, what they do is that they convert the input bits into digital signal. Here, we will convert the input bits into analog signal. By doing that, we eliminate the zero frequency component. So we always confine the composite signal in the bandpass range, in the bandpass frequency range. And in that case, we can transfer these bit combinations over a bandpass channel. Okay? Type. So that's the idea of this chapter. So we will talk about how we convert digital to analog. And by digital here, we mean the input bits, and analog means the mapped analog signal. And we'll talk about four different types of analog transmission schemes. Okay, so we'll talk about amplitude shift keying, frequency shift keying, phase shift keying, and then quadrature amplitude modulation. Who amongst you is familiar with any of these? Anyone familiar with any of these schemes before? No? Never heard of it? Okay, so we'll talk about them. Supposedly you are familiar in a way with these schemes from the signals and systems course. All right, so in this chapter, this is the roadmap of this chapter. So we'll talk about digital to analog conversion, and then we will talk about ASK, FSK, and PSK. And again, these schemes, they try to work on the fundamental properties of any signal, which is the amplitude, frequency, phase. So they are mapped to these three schemes. And then QAM, or quadrature amplitude modulation, what it does is that it tries to combine two of them. to combine the amplitude with the phase. All right? So this is the fourth. By combining two properties, we have come up with a fourth category of schemes. Okay? So the first scheme here is what we call binary amplitude shift keying. So what is R here? R is also 1. We convert one input bit to 1. In that case, it's not a digital signal. In that case, it's an analog signal. Okay? So this analog signal has a certain frequency, which eliminates the low frequency component. So no more of the digital signal. Here we will map it directly to an analog signal, which means that in this case, we can transfer this composite signal over a bandpass channel. So R is 1, and the S in that case is N, the worst case. But the bandwidth is 1 plus D times S, and we'll talk about how is this done. So basically, what this scheme tries to do is that it maps the 1 into a sine wave with a specific frequency, F1, and it maps the 0 to 0. And similar to what we have done before, the 0 is a sine wave with an amplitude 0, right? So similar to what we have done before, this is binary amplitude shift keying, which means that we have only 2 levels. But what we could do is that, again, we can improve that and use 4 different levels by having 4 different amplitudes of the sine wave, right? So in that case, we can map each 2 bits into a sine wave instead of 1 bit. All right. So in that case, only the amplitude of this signal is changed to create this binary amplitude shift key. We call it sometimes on-off keying. On-off keying معناه it's either with 1 amplitude or 0. On-off. That's why it's on-off. So the peak amplitude of one signal is 0, and the peak amplitude for another one is specific positive voltage. So in that case, we end up with a bandwidth like this, which we will talk about how we can calculate the bandwidth like this next time, inshallah. So we want to just analyze the pros and cons of this one in terms of error probability. So basically, this one tends to have higher error probability, right? Especially if you have some attenuation due to the noise on the channel. So if you have attenuation due to some noise on the channel, the amplitude of this sine wave tends to decay. Remember, the attenuation affects the amplitude, right? So if you transfer this over a long line, what will happen to this sine wave is that it will decay. And the problem now is that it will get close to 0. So at the receiver side, you will not be able, because the signal will be something like this. So you will not distinguish this from noise, because also this is due to distortion. The distortion affects the shape, right? So this one will actually become like this. So by adding distortion and attenuation, the one might actually be confused with the 0 and vice versa. So the probability of error here is usually high compared to other techniques that we will talk about. Okay?